most revered Padma Vibhushan Professor M.M. Sharma, Honorable Chancellor Padma Bhushan Professor J.B. Joshi, Honorable Vice Chancellor Vigyan Shri Professor A.B. Pandit, Honorable Director ACSIR Professor Manoj Kumar Dhar, Associate Director ACSIR Professor A.K. Raina, other distinguished people in the audience, my colleagues in the faculty, students, well-wishers and friends, good evening. Indeed, it is my pleasure to welcome all of you to the Dr. APJ Abdul Kalam Transdisciplinary lecture series. Today's lecture will be delivered by none other than Professor M.M. Sharma. He is going to talk about the linkage between chemistry, chemical engineering and chemical technology and how it can be used to benefit the industry. So we are all eager to listen to Professor Sharma. So without wasting further time, let us start with the proceedings. May I request all dignitaries to come on the dais and begin with lighting the lamp. Professor Sharma, Professor Joshi, Professor Pandit, Professor Dhar and Professor Raina. I request all dignitaries to please sit on the dais. dignitaries, may I request Harsha to please welcome Professor M.M. Sharma with a floral bouquet. Now I request Priyanka to please welcome Honorable Chancellor Professor J.B. Joshi. I request Harsha to please welcome Honorable Vice Chancellor Professor A.B. Pandit. I request Priyanka to welcome Professor Manoj Kumar Dhar. Finally, I request Harsha to welcome Professor A.K. Raina. Now I request Professor Manoj Kumar Dhar to take charge of the proceedings.
Good afternoon, everybody. Namaskar. It is with great pleasure that I, on behalf of the entire ACSIR family, extend a very warm welcome to Professor J.B. Joshi, Padma Bhushan Honorable Chancellor, ICT Mumbai, Professor M.M. Sharma, Padma Vibhushan, Academy Professor, ACSIR, and Emeritus Professor of Eminence, ICT, Dr. Swati Piramal, Vice Chairperson of Piramal Group, Professor Chenpati Jagdish, Emeritus Professor, Australian National University, who are our honorable members of the Board of Governors and who are connected online today, Professor A.B. Pandit, Vice Chancellor, ICT, distinguished faculty members of ICT, our distinguished faculty members of ACSIR who are all connected online, other eminent scientists, Professor Avtar Raina, Associate Director ACSIR, colleagues from ACSIR, dear students of ICT Mumbai and students of ACSIR, ladies and gentlemen. We are all here to listen to the fourth lecture in the Dr. APJ Abdul Kalam lecture series to be delivered by Professor M.M. Sharma. So far, 3 lectures have been delivered. However, the present lecture is a special one, as it is for the first time that we are holding lecture under this series outside the premises of any ACSIR associated institute. Before I move ahead, I'll just briefly tell you about ACSIR. ACSIR, Academy of Scientific and Innovative Research, is an institution of national importance established by an Act of Parliament in the year 2012. Just to give you an overview of ACSIR very briefly, we have currently more than 7,000 students who are registered for PhD, which is by far the largest number which any Indian institute has so far as PhD students are concerned, only in science, technology, engineering, mathematics, and medical research. Last year in the convocation, November 2025, we awarded 958 PhD degrees. Our enrollment in the past 5 years has been more than 1,000 students per year for PhD, and last year was a record year. We had more than 1,600 students joining our PhD program in various associated institutes of ACSIR. At the moment, we have 78 campuses, 78 institutes which are associated with ACSIR. We have more than 3,000 faculty members, more than 7,000 alumni since 2012, and more than 29,000 publications which have been made by the students in the last 14 years. And in terms of global partners, we have joint PhD program with 12 universities in the world, and we are 9th so far as NIRF ranking is concerned. Next, please. Yeah. So what we are trying to do is to build a platform, an institution of next generation institution, wherein we were primarily established as an institution of CSIR, catering as an academic arm of CSIR with 38 national institutes called laboratories of CSIR with us. But in the last few years, we have added few more labs of national repute and international repute, like all the 28 institutes of ICMR, Indian Council of Medical Research, and we are shortly going to add up 10 institutes, all 10 institutes of Ministry of Earth Sciences with us. We have few institutes of DST, and obviously we have collaborations with industry, non-government institutions and foreign universities. Together it's a platform, it's an overarching institution which has so many, now it will be 88 institutes. Next please. So as I mentioned, all 38 CSIR laboratories and 28 of ICMR, 5 of DST and 7 other institutes. Next please quickly. And this is the distribution of these labs in the country. You can see almost all parts of the country are covered. Next please. And we offer programs, especially PhD program in several faculties, biological sciences, chemical sciences, physical sciences, mathematical and information sciences, agricultural sciences, engineering sciences and medical research, and programs are PhD in science, engineering and medical research, then several master's degree programs, MSc, MTech and so on. And we have the joint degree programs with several national institutes. We have established an MOU with Indian Council of Agriculture Research also last year. Next. And these are the just a glimpse of the joint PhD program with international universities, 8 Australian universities, including RMIT, University of Melbourne, University of Western Australia, Deakin and so on, and with AIST Japan, University of Turku and Centralis Nantes, France. Today we are meeting here for Dr. APJ Abdul Kalam Transdisciplinary Lecture Series, and as I mentioned, next, the first lecture in this series was delivered by Dr. R.A. Mashelkar, Padma Vibhushan Academy Professor and former Director General of CSIR. He spoke on balancing excellence and relevance in scientific research, lessons from my own book of life. Next, second lecture was delivered by Dr. S. Sivaram, Padma Shri, Honorary Professor and INSA Senior Scientist, Indian Institute of Science, Education and Research, ICIR Pune. And what he spoke was on what you are not taught in the university. Third lecture was delivered by Dr. Sudhir Sopori, Padma Shri, former Vice Chancellor of JNU and presently Emeritus Scientist, International Center for Genetic Engineering and Biotechnology. He spoke on academic journey, reflections on research and lessons learned. And today we are here to listen to the lecture of Professor M.M. Sharma. Now, as I mentioned that we are not on an ACSIR campus today. We are guests here at ICT Mumbai, and I am grateful to the Honorable Vice Chancellor of ICT Mumbai for graciously accepting our request and allowing us to host this lecture here. And in ICT, which has its own extraordinary legacy in chemical sciences and engineering. And I want to spend just 1 minute on why that matters. ACSIR was never conceived as a single campus with 4 walls. It was conceived as a network, a university built on strength of CSIR laboratories spread across the country, bound together not by geography, but by a shared commitment to research and mentorship. There could be no more fitting occasion for this than today's lecture. Professor M.M. Sharma is quite literally a living embodiment of this idea. He holds the position of ACSIR Academy Professor, a title that connects him to our students and our mission. And in the very same breath, he is Professor of Eminence here at ICT, an institution he has helped shape and elevate for decades. His career itself is an argument, perhaps the finest argument I know, for why institutions must not work in isolation. His life's work has been about the union of fundamental chemical science with industrial application, about ideas moving fluidly between the laboratory bench and the process plant, between the academic world and the engineering world. If there is one person whose presence today tells us that walls between institutions are meant to be crossed, it is Professor Sharma. So it is with great pleasure and a real sense of what this moment represents that I welcome wholeheartedly Professor M.M. Sharma to deliver today's lecture. And I thank ICT Mumbai for hosting us with such a warmth. Let this be remembered not merely as a lecture we attended, but as a step in ACSIR moving out and creating bridges among scientists working in our country's finest institutions. Before I request the Honorable Vice Chancellor of ICT to introduce today's speaker, let me say that it is appropriate to reflect on the extraordinary life and legacy of Dr. APJ Abdul Kalam, in whose honor this lecture series has been instituted by ACSIR. Dr. Kalam is often remembered as India's missile man for his pioneering contributions to the nation's space and defense programs. However, his legacy extends far beyond science and technology. He consistently emphasized that scientific excellence must be accompanied by values, ethics, and a commitment to humanity. His vision is not confined to laboratories or institutions. It encompassed a developed, knowledge-driven, and harmonious society. It is in this spirit that ACSIR instituted the Dr. APJ Abdul Kalam Transdisciplinary Lecture Series. The objective of this series is to provide a platform for ACSIR students, faculty members, scientists, and researchers to interact with eminent scientific leaders, technologists, innovators, and thought leaders whose contributions transcend disciplinary boundaries. Now, it would not have been more appropriate than requesting Professor M.M. Sharma to deliver this today's talk. And I'm sure that you will all enjoy, as you have been listening earlier, as I'm told that he very often speaks here. So you must have heard him, but we'll be hearing him for the first time, and all our ACSIR students and faculty, I'm sure they will enjoy his lecture. I once again welcome you all to this lecture, and I request the Honorable Vice Chancellor, ICT Mumbai, Professor Pandit, to please come and introduce the speaker, and also request him to deliver the lecture.
Good evening, distinguished speaker of the day, Professor M.M. Sharma, Professor Manoj Dhar, Professor Raina, Padma Bhushan Chancellor, Professor J.B. Joshi, my colleagues, students, those of us who have had an opportunity to listen to Professor Sharma and learn about his exploits. I don't think ICT requires an introduction of him. But it is obligatory on my part to introduce him. After graduating and post-graduating from ICT, at that time UDCT, Professor Sharma went to Cambridge, did his PhD, and at the young age of 27, when he returned from Cambridge, was appointed as a professor and head of the Department of Chemical Engineering. And since then, he has been associated with chemical engineering and ICT, culminating as a director and superannuating in 1997. Professor Sharma can be considered to be solely responsible to bring up chemical engineering on an international forum. His motto as ideas drive research rather than instruments and equipments has always been a motto. Until he was in ICT, we, the fortunate ones, have always had benefit of this vision as this essential modality of carrying out research. Professor Sharma is most well respected in every field of chemical engineering. He has served on multiple government committees. He has served on multiple educational committees and has been associated with CSIR since the past 60 years or so. So this itself tells that he is the most suited person to give academic talk, and the title of the talk which he has chosen is definitely going to enrich you in terms of how and one paints a bigger picture on a larger canvas, listing out what is the current status, what has been the past, and what is the future which the people involved in chemical engineering, chemical technology, and in general chemical sciences can expect. I in fact told my students that even though you are in the middle of mid-semester examination, I requested that take 1 hour out and listen to Professor Sharma, and I'm really glad to see this KV auditorium full and overflowing. Those who are standing at the back can find places or can sit on the steps if you are comfortable doing that, and take whatever Professor Sharma says in full spirit, as well as think about what he says, how he has been able to formulate his thought process, and how eager he is, even at the age of 90, to converse and interact with the students. It's for us a permanent inspiration, and I request Professor Sharma to give today's APJ Abdul Kalam lecture.
Professor Dhar, Professor Raina, Chancellor Professor J.B. Joshi, Vice Chancellor Professor A.B. Pandit. I am grateful to the Academy CSIR to invite me to give this Abdul Kalam lecture. I worked with him on the first TIFAC committee, and one of the difficult jobs we handled right in the beginning was sugar industry, because that comes under so many ministries. And many of you would know that many improvements in sugar industry came out of the recommendations of that committee, particularly cogeneration. There was hardly any sugar factory in India having cogeneration. There are many sugar factories today which make more money selling power than selling sugar. I am also very happy to give this talk in this very auditorium where I used to, as a student, listen to lecture. And this institution epitomizes my title, because right from the beginning, chemistry, chemical technology, chemical engineering in industry orchestrated. Later on, fairly few years, some few years after UDCT was created, biology, and lately even physics. And I'll explain to you why orchestration with biology has to be done and also with physics to be done as I develop my theme. I am going to start with APIs, active pharmaceutical ingredients. Because India is pharmacy of the world, and I'll tell you the plus and minus point. Normally, they are chemistry dominated. So the chemistry people think very differently. They don't realize then when that particular API is to be commercialized, what are the problems they would face. So one of the motto which I have championed and practiced with the industries with whom I have been associated, I've been associated with industry for more than 60 years, that you should have what we call rowing exercise rather than relay exercise. In relay exercise, you go, chemist develops, he goes to chemical technologies, goes to chemical engineer. So far as industry is concerned, most of the pharmaceutical people work on this particular drug which is going to go out of patent. So for them, identification of a product is not that difficult as a normal chemical industry, about which I'll refer later. So this has been heeded by industry, and normally now chemists, chemical engineers, chemical technologists and industry people work together, and whenever there is a problem of biology interest, biologists are also included. Physicists normally are not involved in the API part, but I'll refer to area where they become relevant, but it interfaces with chemistry. So let me start by dramatizing a situation. An API has been developed, plant has been put up, chemistry is right, product is not sellable. Why? Particle size is not right, particle size distribution is not right, bulk density is not right, loss on drying is not right. Plant is already there, huge investment has been made. What next then? Now, if they are taken care from the beginning, that you had studied, most APIs are crystallized, that you had crystallized properly. And there is of course the problem of polymorph also. Some polymorph which is not stable, and there are occasions when you need a product which is 100% amorphous. Even 2 or 3% crystalline product will not be acceptable there. How do you ensure that you get 100% amorphous material? Talking about a very simple chemical industry problem, you are all familiar with precipitated calcium carbonate. You use it every day in the morning in your toothpaste. But what people don't realize is when I carbonate a slurry of lime, whether I will get calcite or other crystalline configuration is a matter of detail. Whether you will get witterite or you will get aragonite. So how do you change conditions that you get only calcite or you get only aragonite? Now chemistry is simple. What is you can't go wrong in reaction of carbon dioxide with calcium hydroxide. You put up a plant and your product doesn't meet the particle size distribution, you will have problem. Your crystalline form is not right. Then what happens in most of these APIs, you have a problem of multiple steps. So very often 5 tons of unwanted material are associated with 1 ton of the material, sometimes even 10 tons. Some occasions even 20. But 5 I can take as that. So what happens to that? The chemist is very busy seeing that chemistry is right. But that doesn't lead to the commercialization by itself. So you have to take into account how do you deal with this, and pollution regulations are very tough, particularly with nitrogen containing compounds, inorganic plus organic. So in the very beginning, you have to deal with the way, that is why the interdisciplinary part comes in. How will you deal with the effluent coming? That should be part and parcel of the development, which is many times ignored, particularly with nitrogen containing compounds, I tell you. Of course, in the recent past you found the nitrosyl oxide was a very serious problem, and it went to the ppm, ppb level of nitrite in water. You know, when you don't look at the problem in integrated way, you can land into a very peculiar problem. And it's very severe competition. So one company is always gearing to find out ways by which the competitors can be put out. So bring in new, like nitrosamine should be below few 4 parts per billion or 5 parts per billion. I refer to the polymorph problem. There have been many legendary cases in industry that the polymorph was not stable. Abbott went through this game. Now there are ways and means of predicting polymorph. You have to make sure that your polymorph is stable. I'll now deal with how do you deal with all things which are left out after you got your molecule. So when you ask a person, you crystallize, so what is the solubility in the solvent? So typical answer would be insoluble. I say, what do you mean by insoluble? You had 10 times dilution. If you had 0.2% solubility even, it is 2% of a very valuable component. Often it is more than that. Then of course they'll get little invigorated and they'll say, all right, we can take second crop. Now how do you recover the solvent? Chemist doesn't apply his mind. You are having dilution typically 10 times. And solvents are not cheap and solvents can't be discarded. And 80%, you know, when you do some preliminary study, you say 80% recovery is just not acceptable. You want 95% plus. How do you ensure? Now, there are new techniques that have come which can make the recovery very benign. And I am referring to use of nanofiltration. Nanofiltration allows molecules which have molecular weight more than 250 at ambient conditions. And we have polymeric material today for nanofiltration which can stand as potent polar substances like DMF, DMAC, and they are commercial. So when I happen to first refer to use of nanofiltration in one of the very famous APIs, I will not name either the company or the product, but take for me, there is a real case. At that time, nobody was using nanofiltration in India. So it didn't cut ice. 3 years later, exactly on same item, GSK had a patent. So I had occasion to slam it on them, say, look, you didn't listen to me. I'm mentioning this because there is a very peculiar disease in India. I call it disease in industry. Has anybody done in the world this? Can't we be the first in the world to do something? And it requires a lot of persuasion, what I call, way people do conversions, that kind of gusto you have to convert people. Once somebody has done, so in alcohol industry what happened, azeotropic alcohol to be converted to absolute alcohol for blending. When the first person started using zeolite, then say, wo kaam kar raha hai, let us do that. And when per vibration started, then people. But the first one has to face the drama. And it is here where you take it for granted in India. Anything you do will never be hidden, no matter what you do. It will spread. Fortunately in pharma industry, process patent is respected because competitor is not able to follow what has been patented. That is one rare. Otherwise, in other branches of chemical industry in India, people are not able to. So I have mentioned about how we use. So you are making use of the good chemistry. Another problem that chemists face, they will use reagents and conditions not realizing they are very difficult. I'll give you an illustration. Let's say we are using nitromethane. I remember one very eminent chemist saying that he has got a revolutionary process for ranitidine. I said, look, with whatever understanding I have, you please explain to me. I said, you have not realized the hazard. Get a reaction calorimeter run. Behold, he found runaway conditions. I said, you might think your process was revolutionary, but it will be counter-revolutionary in terms of implementation. So the moral of the lesson is you have to take care of the safety part right from the beginning. Don't adopt conditions which are hazardous if you can. For example, if I want to do addition of SCN, now you can in principle generate from sodium cyanide and sulfuric acid and do, let's say, a carbonyl compound addition with SCN. Instead of that, it's much better to use acetone cyanohydrin to transfer SCN to your carbonyl compound. We did this in in the very beginning. The problem is most organic chemists do not know industrial chemistry. I'm not criticizing them. They do a wonderful job. So they don't know that acetone cyanide is a multi-million ton product. It's available at a very... And then transfer of SCN from acetone cyanohydrin to carbonyl compound. With the developments in enzymes, you can get optically active cyanohydrin. That can reduce the cost of your final product drastically, because instead of racemic, you are getting optically active. So this is yet another very important area of doing asymmetric synthesis, because the resolution of the racemic compound cost and the price difference, even if you take a common item like 2-aminobutanol, D2-aminobutanol versus racemic, the price difference is 2.5 times. And what do you do with the unwanted, which you cannot re-racemize? That is another big challenge that you have. And when you have nitrogen containing compound and unwanted isomer doesn't have a market, how do you valorize that? Now, if you don't account for that in the beginning, you will be stuck with the problem in the end, that how did you dispose? You don't want to burn some molecule, no? So these are some of the things which you should... I now come to biotransformation. Now, biotransformation, getting the enzyme, of course, is very, very important. But where do we fail? It is in downstream. And UDCT took a pioneering step in having this MSc Tech Bioprocess Technology course concentrating only on downstream processing, because 80% of the investment is in downstream processing. Of course, it's irrelevant if the enzyme didn't work. But even if enzyme works, and I know of an actual case of lactic acid in India where fermentation worked and the downstream failed. A lot of money went down the drain because this couldn't be commercialized. Now, these are kind of things where I said this, if you don't do the orchestration from the beginning, you will land into these kind of problems, because superficially it looked very attractive, but it couldn't generate. I will also give you example of a very odd kind, which we would have rarely come across. I think this doesn't have a stopper. It doesn't matter. Mine is plastic one, thanks to the plastic things which don't break, This, when you do this fermentation, and of course this is, I've been championing with ICT, that we should really do work on directed evolution of enzyme. Francis Arnold's Nobel Prize winning, it has made an extraordinary difference for making intermediate for sitagliptin and for Lipitor. The cost would be something like 30% of the normal process, even less maybe. So we need to develop in India, so we would need now orchestration with two types of people. People who are very good in biochemistry and people who are very good in computational work. When you say directed evolution means you need, I regret to say that both the sides do not have the strength that we ought to have in India. Either in terms of directed evolution or on computational work. You will be surprised that so much is being talked about IT and all in India, but we don't have this complicated computational work required for directed evolution of enzyme. Hopefully, in coming years, ICT will equip itself both for directed evolution enzymes as well as the computational work. I will now refer to all examples I am going to give you are live, something which I have practiced with due modesty. I will now give you some very interesting examples. You are all familiar with phosgenations. Phosgene after the Bhopal disaster is not allowed to be sold, it has to be used within the plant. Before that, phosgene cylinders were allowed to be transported in India. So after Bhopal disaster, I happened to head that committee. Government wanted to ban manufacture of phosgene. And you know how pharma industry requires chloroformates, benzyl chloroformate, so many chloroformates they require. How polymer industry wants isocyanates, TDI or MDI. So most of the phosgenations that you do, either to make chloroformate or acid chloride or isocyanate, all of them have relevance in varieties of industry from polymer to pharma and even agro. You need excess phosgene because otherwise you are not able to drive. Now how do you deal with the excess phosgene? So when you are developing the process, you find it very convenient to just destroy by scrubbing in caustic. Mind you, COCl2, 4 moles of caustic you end up with. Realize it's not cheap. Caustic soda is also 35 rupees a kilo. People forget, organic chemists forget physical chemistry. They didn't know the kinetics of phosgene hydrolysis, that at ambient condition, half-life of phosgene hydrolysis is 1/25th of a second. So major part of the phosgene that is in excess can be just demolished by water washing, and you save so much of money using caustic soda. But finally, you have to have in the final exit carbon dioxide phosgene at 1 ppm level, and you have detectors. How to deal with that also, otherwise carbon dioxide, if you have to absorb in caustic, even to take care of 0.2% phosgene or 0.1% phosgene again adds to your cost. So there are ways and means of dealing with that. I already referred to FDI doesn't allow any drug or any agrochemical to be marketed. If it is racemic, they have to show the activity of the optically active molecule. If you don't succeed in doing asymmetric synthesis, then you have to do resolution. And this resolution must be done smartly, and you must look at the ways and means of unwanted isomer to be converted through racemization. If not possible, valorize that. Otherwise, more than half of your molecule, you are sitting pretty. So this is a very important challenge which requires collaboration. I will now go to some different examples that how dynamics of industry can influence novel processes. And I'll name the product because it met that fate. There was an old vinyl acetate plant. See, in earlier days, many plants that we had put up in India were of capacity nowhere near contemporary. So this was like a 25,000 ton plant which was taken to 32,000 ton plant, but global capacity minimum 100 if not 300,000. So the challenge for people to orchestrate is how to use plants which were designed for a certain product to be used, particularly continuous plants. Batch plants are easier to adapt from one product. Suppose you are doing nitration of A, you can do nitration of B. Maybe some small modification here and there. But why do you do in continuous plant? So we managed to instead of doing acetoxylation of ethylene, we did acetoxylation of propylene to make allyl acetate and hydrolyze allyl acetate to allyl alcohol with cation exchange resins. That also is a good model. Many times when you develop processes, you use homogeneous catalysts. And you then end up in problem of removing that homogeneous, let's say in acid catalyzed alkylation. You use a homogeneous catalyst, you have to wash it. Along with the wash, you lose the important molecules also, and that creates also problems of disposal. Suppose you are doing toluene sulfonic acid. It is not treatable in effluent. Cation action resins can do this job very elegant. We did this work in early 80s and commercialized. I told you, I'm very well placed to talk about the title of my subject because this institution across the board has practiced combining chemistry, chemical technology, chemical engineering and industry, and now heading towards bringing biology and physics. I'll talk about a little more about physics shortly. So this was done very well. Technology has succeeded admirably. It's a very tough job to converting a continuous plant from one product to another. It's not like one nitration replaced by another nitration. No. The dynamics of pricing of product in India is so, or globally, you can see not only during COVID time or recent war in West Asia, acetic acid can go from 28 rupees to 80 rupees. So this met that fate, that it was based on a certain product profile. So here is an example where technology, plant very successful, commercially unsuccessful. Great achievement in terms of, the lesson is that you have to take into consideration the dynamics of industry, how prices can change, and do what we call sensitivity analysis. That if the price changes, where would we be? Of course, there's something else in India we have to say, that no matter which plant you put up, it will be chorrowed if it is giving decent margin, without fail. It may take 2 years, 3 years. So how do you protect yourself? You are not able to protect to patent. The only way you can protect is by capacity and relationship with customers. That is very important. Otherwise, you did all the work of developing a technology and it has been taken overnight, clandestinely by. This is a real story in India. I'm not hypothesizing. And you have to guard against that. Why I'm mentioning that? You have to guard against this when you. Then now you are a new addition. How will you compete internationally? Because we are signing agreements, free trade agreement. How do you put up plants, even though you have done all this orchestration? What sensitivity analysis you have done to ensure that you are going to succeed? So I'll come to now effluent treatment. Treatment, when I used to interact with Niri, they will only talk about destroying, like what you do with municipal. I said, why don't you look at valorizing? Now it's highly relevant in pharma and agro industry, pharma in particular. I told you 5 kilos per kilo of wanted material, 5 kilos of unwanted. Now many of these molecules are untreatable, they are refractory, aromatic molecules. Let's take aniline, take morpholin, going in affluent. If you didn't factor that in the beginning, now why treat when it's not treatable? Why not recover? So we have live examples in pharma industry where tens of crores have been recovered through not only recovering these molecules but also creating problems of inability to treat the effluent. You don't meet. Now old days that you could manage effluent is gone. Today public itself is so smart and environmental agencies have also become smarter. So you ask for the fate of every molecule. Because when you give the consent, you ask. I think some people from ICT are involved in the pollution board clearances and all, Very difficult for people to hide. So my suggestion is all these cases, there is no molecule which is cheap. So solvent recoveries were hardly done properly, 80-85%. How can you, where does, will you believe today 100,000 tons of methylene chloride is used in pharma industry? 100,000 tons per annum. Why? So I'll give you a live example and how chemical engineering is brought. You are doing reaction at minus 70 degrees by direct injection of liquid nitrogen. When it leaves at even at minus 30, still there is a good vapor pressure of methylene chloride. So you are not only losing that methylene chloride, you are creating an atmospheric hazard. So the chemical engineering tells you that why you want to do by direct injection, put proper coil, and therefore all the loss of methylene chloride is completely prevented. It is economically attractive. But to convince the user in the beginning, he says, hoega, nahi hoega. I said, look, principles of chemical engineering are there, that I have know what sort of heat transfer coefficient I'll have, this is the coil area I have. There is no reason why it won't happen, and it has happened. So don't underestimate solvent recovery problems even from, now methylene chloride, 1.8%, 2% solubility in water. You can't let it go. So chemical engineering tells us that you can do steam stripping. So an uninitiated person, 2% methylene chloride in water, steam stripping, what will be the energy cost? But they have forgotten principles of thermodynamics, highly non-ideal. Fact that solubility is no means highly non-ideal system. So actual net consumption of steam per ton of methylene chloride that you recover may not be even 2. And this can all be recovered. But I regret to say that India is using 100,000 tons per annum of methylene chloride. Of course, people making chloromethanes are happy because they have so much consumption. All solvents which are used, if they can be recycled, the manufacturer will suffer. The pharma industry will gain, and there are many examples of this kind. I will now move to bulk petrochemicals because I don't want to only talk about organic chemical industry. I will now refer to certain problems that we have where this kind of orchestration is required. Sometimes even adopting, for example, if you had a polyester has gone in such a big way that you don't talk about, so you would have heard Reliance's recent announcement that they will have PTA, purified terephthalic acid, plant 10,000 tons per day, 10,000 tons per day continuous plant. Now, in the beginning, what was the capacity that we would have 40-50,000 tons per annum? Now, what do you do with that plant? So the analogous thing is instead of paraxylene to terephthalic acid, use metaxylene to isophthalic acid. And the plant that you had put for paraxylene, for mixed xylene, with the modification of zeolite, turn that plant. Reliance has done that in Patalganga. That they had small capacity PTA plant in relation to the latest plant they are putting is converted. Here is an example of adopting a plant for a product and then to be taken for a related. So this is something we keep on encountering every now and then. To that I will add one more problem where this orchestration is required. How to sweat plants. More from less, less for more. How can I get, plants might have been there and the company which has given you know-how, project engineering, let's say the plant was capacity X. That fellow keeps some safety. So we have one example of phenol plant at 2 lakh tons per annum taken to 3 lakh 20,000 tons. Same plant. How do you do that? It's not run-of-the-mill problem. To sweat plants, you require in-depth knowledge because today you are talking of every product not on the basis of purity. You only talk of impurity profile. Purified terephthalic acid name itself incorporates purity. Purified is the only molecule where the first word is purified. So pharma, nobody talks of the purity, only say give me the impurity profile. So this is a very tall, in a PTA plant, the investment that goes in taking care of the aldehyde impurities during oxidation takes up a big chunk of money. The challenge for all the persons who are working in this area is how can I tame my conditions for paraxylene oxidation by which I can prevent formation of carbonyl compounds. That is aldehyde, which affects the quality of the textile fiber, polyester fiber. You will not have any terephthalic acid even having 20 ppm of terephthaldehyde or monoaldehyde. So the kind of challenges that you have in large scale plants are very different from the challenges that you follow in pharma industry. I will now turn my attention to recent awakening of using Fischer-Tropsch synthesis. Fischer-Tropsch, as you know, was invented in the 1920s by German Fischer and Tropsch, and widely practiced in South Africa, because when South Africa had apartheid, they thought they will have naval blockade and therefore they will not get any petrol. They had no petroleum. So they perfected Fischer-Tropsch. What is the versatility of this Fischer-Tropsch and why you need orchestration between chemists, chemical engineers and industry? And I'll explain to you why. Syngas can be made from any way. CO plus hydrogen, you can do from methane, you can do from naphtha, you can do from agro waste, you can do from coal. So you have multiple sources of making syngas. CO plus hydrogen, and there will be some CO2 in it. How to convert this into valuable products? The original aim of Fischer-Tropsch was to make only fuels, particularly diesel, whose cetane number more than 70, whereas normal cetane that you get from petroleum refinery 50, 52, 53, thereabouts. So small blending of Fischer-Tropsch diesel would boost 48, 50% to 52, 53% to great benefit of petroleum refining industry. And you want now today better and better products. Now how do we deal with this problem? And what is the way by which this Fischer-Tropsch? I will tell you 2, 3. Now people know that I can use fixed bed reactor, I can use slurry reactor. When it came to slurry reactor, the South Africans were smarter than Shell, which also had expertise in this area. And please listen to what I am going to say. They have giant size slurry reactors operating for Fischer-Tropsch. It's a very tough problem because you have high loading of the catalyst, and catalyst has very high density, typically iron, nickel, cobalt. How do you design? How do you make sure? Now you did the work in the lab scale and showed that by this catalyst I can change the product profile. Today you want to operate Fischer-Tropsch in petrochemical mode. That is, I don't want to make only, I want to make olefins. That itself is wonder. Now I come to catalysis. Don't you think it's a wonder that you are able to combine CO plus hydrogen to whole range of products? Only methane, only methanol, only hydrocarbons. But now we are talking of olefins and alcohols. And Sasol is marketing pentene 1, hexene 1, octene 1 from Fischer-Tropsch. What did it mean? What collaboration was required? How do you remodel your catalyst, which instead of polymerization of CH2, in fact, for people who are interested in catalysis, the brilliant example of surface migration is this. If methylene did not migrate, you will not get polymethylene, you will not get diesel. Surface diffusion, because it otherwise looks like a funny concept. But this is a brilliant, simple example to tell you how surface diffusion is important. So it required development of the catalyst. Now catalyst development is one where you need orchestration between chemists, chemical engineers, material scientists and physicists. Because characterization, you want stability of the catalyst. So I'll give you a classic example. Naphtha reforming to make syngas. People knew that nickel catalyst works, but it would get fouled in no time. So you did lab experiment and showed, oh, nickel catalyst worked very well, but it failed in the plant because they were carbon layer. So catalyst formulation requires material scientists, involvement of chemical engineers. The chemists had done a brilliant job of developing the catalyst which worked on the bench scale, but to convert this into industrial operation, I want stability of the catalyst. For example, in an ammonia plant, you don't shut ammonia plant for 3 years. So you want every catalyst for ammonia synthesis to work without any fouling for 3 years, because it's highly capital intensive plant. So the Fischer-Tropsch provided a brilliant example of designing large scale, whether fixed bed reactor, slurry reactor, development of novel catalysts, catalyst characterization. Every type of spectroscopic method is used in catalyst development today. Now without, and in fact if you see any journal, there are plenty of journals in catalysis, from Journal of Catalysis to Applied, you will find papers coming from chemists, chemical engineers, physicists, and if it is enzymatic, you will find biologists. It shows very nice orchestration between chemists, physicists, material scientists. Catalyst development is not an easy job. It's very easy to publish a paper, but to get a stable catalyst which works in and out all the time, at least and that you have a protocol of regenerating that catalyst, because to remove that catalyst and put a new catalyst not only cost, but you lose production. Something similar has happened in cat cracking. Catalytic cracking was developed. That was the first outstanding example of fluidized bed reactor in the history of chemical engineering. And the odd part was fluidized bed reactor operated during wartime without understanding how fluidized bed reactors work. But they delivered the goods. It took many years to have this two-phase theory and all that. Now this fluidized bed reactors application transformed the whole cat cracking. All heavier petroleum fractions, how you upgrade them into valuable components. So you got more, America is always hungry for gasoline, what they call gas. We were hungry for diesel, because we are more diesel-centric country than gasoline-centric. Now how to convert a cat cracker into maximizing diesel required the kind of collaboration I am talking about. But today we have gone one step further. We want to operate cat crackers in petrochemical mode. How do I summarize in very simple word? Formerly when we were operating cat cracker, propylene yield was 4%. Today we have gone for 18%, and there are chances that we will cross 20%. This required catalyst development. How you modify zeolite catalyst, how you can promote. So very high science is involved. Delivery looks final and thing looks simple, but you don't know the kind of design that was involved in this cat crackers. What was the design of the catalyst which allowed the just like Fischer-Tropsch in petrochemical mode, cat cracking in petrochemical. The next candidate will be hydrocrackers to be operated in petrochemical mode. So these are the things where collaboration is an absolute necessity. So what do we take from whatever I talked about? First of all, we have to give up ego. Why I am saying this? Chemists will say, oh, my process is right, you damn fellows, you have messed it up. The chemical engineer will tell, all your chemistry was all wrong, it was okay. By the way, they keep on using round bottom flask. Ban round bottom flask because mixing, one of the biggest problem in fine chemicals, pharma industries, lack of understanding on mixing. So we have got two wizards in mixing here, both Joshi and Pandit. They have taken care of many problems, very critical. But you do in a small lab reactor, it's okay. It's not ideal. But round bottom flask is absolutely negative because there's hardly any mixing you can get in a round. So they will always say, oh, I've done this experiment, round bottom flask, RBF, I said, that's one thing you should ban, put a board. No round bottom flask to be used. Why I'm saying that he didn't orchestrate between him and the fellow who is going to commercialize. So you give up ego. Developments do not take place when you take egoistic. Never use the word, I did it. Always say that we did it. And lastly, I will say, how do you survive as a consultant? It's 30 years since I superannuated from UDCT then. I'm still interacting with industry. With one, that when something fails, because we have a very peculiar problem in India. We have a cultural problem, we never own failures. And no development takes place without failures. If somebody says all my ideas were right, he's telling blatant lie. Or he was doing very routine. So my motto was simple. When something doesn't work, he said that Sharma gave this idea. And that solves 95% of the problem. Take it from me. So always use the word we. You want to orchestrate means not I. We have done it. That we all work together, we own it together, success as well as failure. May I once again thank the Academy CSR with whom I have had association from the beginning. Like CSR, you were told I have association of more than 60 years. There is hardly any lab of CSR spread throughout India which I have not visited. And I have been involved in many of research councils of CSR laboratories. So, and this institute, including Venkatraman, was the first Indian director of National Chemical Laboratory. And several UDCT people have been directors of so many CSR labs. Such a small institute. Ramarao was UDCT product. R.V. Mitra was UDCT product. Mashelkar UDCT product. Nityanand UDCT product. Vora, who started IMT, UDCT product. One man in metallurgy, Altekar, became director of NML. There was only one person in metallurgy in UDCT. Even then he became director of NML, Jamshedpur. So kudos to this institute. Very ably you agreed to have my talk here because I feel very comfortable simply because the topic which I have chosen is very well practiced here. So it is not a dry talk, it is a wet talk. Thank you very much.
I now request Professor Dhar to felicitate the dignitaries on the dais. May I now request Professor Pandit to give a small token of appreciation to Professor Dhar and Professor Raina. May I now request Professor Raina to deliver the vote of thanks.
What could be the best acknowledgement of such a wonderful lecture, particularly to young minds? May I request you to stand straight on your chairs and close eyes for 30 seconds. Just put all the material that Professor Sharma has fed you in your thistle and see how much does precipitate at the bottom. I think that can be the best gratitude to a series of teachers. I think we have 3 generations on the dais itself. It is very difficult to say any vote of thanks even. But couple of things I want to say. We have a tradition of Guru Shishya Parampara. And there is also a saying that Guru ke aage nahi chalna chahiye. And that's why I do not intend to indulge in anything, but let you introspect on what Professor Sharma has said. Number second is, it has to be a process of learning as the parampara we have, that is, that we inculcate from the word Upanishad, the greatest texts ever produced. Sit beside and listen. That is the short meaning, but for those cutting short, I'll like to say that Professor Sharma has rather हमारा इतना ज्ञानवर्धन हुआ है कि it's very difficult to say anything, to be very frank. And thank you, Professor Sharma, for being with us, accepting our invitation and presenting such a wonderful lecture. We are thankful to Professor J.B. Joshi, who could find his time to be present in this auditorium. And we are also thankful to Professor A.B. Pandit for all his love, affection, I think. And that is why it all happened in this auditorium that fortunately has been inaugurated by Professor M.M. Sharma itself. So towards the end, I will say that there is a lot of hard work at the back end of any small or larger program. And it is thanks to all those who have come here to listen to this program, and some of our even board of governors people are also members, respected members are also there, Professor Chennupati Jagdish, Dr. Swati Piramal, Professor Vijay Mohan Pillai. I thank them all also for being with us. I thank all the students and faculty members who have joined here offline and online also. I think there must not be less than 1,000 people listening to this lecture. I am thankful to Professor P.D. Yadav and Professor Sachin Yadav and Professor, I think I have heard few names. Professor Vaidya, who have been at the back end of this program, who have made this program successful. I thank one and all, and our team from ACSR who have been working very hard on this lecture. Thank you so much. So nice of you.
Now I request all of you to stand up for Vande Mataram.
Vande Mataram, Vande Mataram, Sujala Sufala, Malayaj Sheetala, Sasya Shyamala Mataram, Vande Mataram, Shubhra Jyosna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Now I invite all of you for high tea outside. Please join us. I would request for a photograph. A group photograph